How's it going, everybody? And welcome back to our Cisco Enterprise series. I had to think about that for a second. So in this video, we are going to be doing the layer 3 configuration for the switches in the campus LAN, so switch 7 and switch 8. And then I'll also be setting up high availability in the VPC for the Nexus environment. So the goal here is to set up HSRP. I'm going to do HSRP in both locations. Configuration wise, it's pretty much the same. Again, I'm not here to show you a really major difference between iOS and Nexus. It's more or less just to set up the default gateways, because eventually we're going to need to advertise those subnets into EIGRP and OSPF once we get down to them. So with that being said, I'm going to go ahead and deploy SPIs to both switch 7, switch 8, and Nexus 50 and 51. We're going to get those configured, and then we're going to go ahead and set up the IP addressing here on all these devices. So we're going to be configuring gig 1 on these devices and E15 on these devices with IP addresses so that we can do dynamic routing once we get there. So without any further ado, let's go ahead and dive into the config. So on switch 7, I'm going to go ahead and I'm going to type in interface VLAN 10, and I'm going to set the IP address here to 10.1.10.7/24, and I'm going to no shut that. And then do the exact same thing for VLAN 11. And do 11, no shut. Alright, now that we have that done, we're going to go ahead to the next stage and do the same config on switch 8. We're going to go to interface VLAN 10. Now, some of you might have noticed this. Alright, so I'm going to go ahead and give the IP address here, which is going to be 10.1.10.8/24. And I'm going to no shut that interface. And then we're going to do the same thing for VLAN 11. We're going to set the IP address on this guy, and then no shut that. There's a question. How come I'm using .8 and .7 instead of .1 and .2? The answer to that question is actually very simple. Normally you would use like .1, .2. Typically, so depends on what the default gateway is for the subnet. So normally in this case here I don't have to worry about it, but in a real world environment you might have to be cognizant of that. So let's say the default gateway is set to .1. It's a very common gateway. I actually prefer .254, but that's just me. So you do .2 and .3, so you're, whichever device gets it. If you're doing a scenario like this, if you're dealing with chassis aggregation, like a stack, you wouldn't need to worry about it because both devices wouldn't be getting an IP address. So if you have a situation where you do have two physical pieces of equipment and you give an IP address to both, you would give .2 to one, .3 to another, and then you give the virtual IP .1, and then .2 and .3 would share ownership of .1, depending on who's the active box in the network. So that's how you normally would do it. I am choosing to do .7 and .8 because I've got switch 7 and switch 8. Over here, when I do HSRP, I'm going to do .50 and .51, just so that it makes sense, so that I know my gateway will always be set to .1, and I'll always be in good shape. Or .254, it really depends on the situation that you're dealing with, but that's typically how you would go about doing that. So now we've got that. I'm going to go back over here to interface VLAN 10, and I'm going to type in here standby, so HSRP configuration, standby, and it's going to be group 10. And then the IP is going to be 10.1.10.1. And I'm going to put over here the priority is going to be 150. So for VLAN 10, I want all traffic to go to switch 7. And then I'm going to go over to switch 8 and do interface VLAN 10 and type in standby 10 IP is 10.1.10.1. And I'm not going to do anything in terms of the priority, because I want switch 7 to be the active forwarder for this. So if I do show standby brief, we're going to see once switch 8 starts participating in connectivity, which usually takes about a moment. Switch 8 is, there it goes. So it's about 10 seconds or so that you have to wait. So if I go back over here to switch 7 and hit the up arrow, now we're going to see 10.1.10.8. It's the standby. So it's active standby is the role. So we're in good shape there. So now that we've got that done, I'm going to go to interface VLAN 11, and I'm going to make 8 the active guy for VLAN 11. 7 will be the standby. So you might ask, how come I didn't just do, VLAN 11 on this one is the active, and then VLAN 10 over here, because the numbers make more sense. Put the even VLAN on the even device. You could do that. There's nothing wrong with it. I am trying to be a little bit of a rebel at the moment and going a different path. That's all. So I'm going to type in standby 11 IP is going to be 10.1.11.1, and then I'm going to go over to switch 8 and do interface VLAN 11. Standby 11 is going to be IP 10.1.11.1, and then the priority is going to be 150. So now that we have that in play. So we'll give that a moment. It's in listen mode. There it goes, it's active. So do show standby brief. So we're still waiting for 7 to cooperate. So why is 7? Okay, there it goes. It's just taking longer than I expected. Okay, cool. So we're good to go there. So that's essentially what I wanted you guys to see in terms of standing up HSRP on that. So and it just dawned on me now that I haven't gone through and explained how HSRP works. So this is a gateway redundancy mechanism for first hop redundancy. So FHRP is a first hop redundancy protocol, and essentially what that means is you have two different devices, two physical pieces of equipment that are, and it could be technically two stacks depending on the size of your environment, but two physical pieces of equipment that are at the edge of your environment. So typically going to be your distribution layer, and that's going to be the devices that are going to get the IP address of the gateway that all of your endpoints that are southbound, so all of this, are going to point to switch 7 and 8 for exiting their network. So the key thing that I want you to keep in the back of your mind here is that the communication between these two devices needs to be layer 2 first and foremost. So these guys have to be layer 2 adjacent with each other. So having the same VLAN, they need to have an SVI, a switch virtual interface, for each VLAN. And then you need to go underneath each SVI, interface VLAN, and configure the standby configuration for both of them so they both can participate in HSRP and so they can communicate with one another. Now I'm going to go into a lot more depth once we get into services, but I didn't even realize that I hadn't talked about HSRP yet. So this is one of those times where I'm kind of putting the cart before the horse just a little bit, but getting the configuration wise, getting it stood up. So what we're going to go do now is on N51 and 50. So I'll go back and I will whiteboard. I'll probably edit this video and I'll do explain how HSRP works. You could also use VRRP. So HSRP is a Cisco proprietary version, and VRRP is your open standard. So if another vendor wants to do anything similar to HSRP, they have to deploy VRRP in order for that to work. So that's going to be, so Juniper or Arista, they have to use VRRP, so the Virtual Router Redundancy Protocol. So I'm going to go ahead and jump over to Nexus 50 and 51. We're going to go ahead and log into them. And then I'm going to go to Global Config, and I do a show run pipe include interface. I'm sorry, the feature, that's what I meant to say. So we want to make sure that the feature interface VLAN has been added, which it has right here. And that's going to be how we're going to be able to create an SPI. So I'm going to type in, and now I have to turn on the feature. You know what? I did HSRP over here. Let's go ahead and do VRRP here. Basically the same thing, just a slight difference. So I was going to turn VRRP on that box, and I'm going to log into here. Feature VRRP. There we go. Now I'm going to jump back over here to 50. I'm going to do a show VLAN brief. We have VLAN 20, so interface VLAN 20. I'm going to set the IP address here to be 10.1.20.50/24. I'm going to no shut this guy. Same thing on 51, so interface VLAN 20. IP address here is going to be 10.1.20.51/24 and no shut. So if I show IP interface brief, I have an SPI up, and if I ping 10.1.20.51, once it ARPs for it, I can ping back and forth, which is exactly what I'm looking for. So what I'm going to do now is on 50, I'm going to go ahead and underneath here, I'm going to type in VRRP, and then the group number is going to be 20. And then I'm going to hit the enter key. I'm going to go under VRRP subconfig mode and type in address. The address is going to be 10.1.20.1. And I'm going to set the priority to be 150. Then I'm going to go over to 51. I'm going to type in VRRP 20. I'll say the address is going to be 10.1.20.1, and that's all I'm going to have to do. So I'll just do a show VRRP brief, VRRP summary. Actually, VRRP there we go. So it's initializing. It'll take a couple of moments for it to trigger, but once it does, we'll be in good shape. So actually, you know what? I think I need to no shut it, don't I? No shut. Yes. No shut it. That's one thing I forgot about. There we go. So if I show VRRP, there we go. Perfect. So now it's working the way I expect it to. So that's where we are at with that. So now that we have that configuration in place, the next step for me to go through and do on all this equipment, now we have VRRP and HSRP deployed, is go through and get all of the LAN connectivity from these devices configured. So E15 and then Gig 11 on all devices. So since I'm already on Nexus, I might as well knock it out here. So I'm going to type in show interface status. And we can see the E15 right now is turned off, but it's a routed interface. And that's exactly what we want to have. So I'm going to go to interface E1/5, and I'm going to specify IP address here is going to be 10.25.51.51/24. And I'm going to no shut the interface. Now there's another question. How come I am using /24s? How come I'm not using /30s as you normally would as a transit interface? Simple. This is a lab environment, and I am not digging into /30s. You would in the real world, yes, but in a lab environment, /24s are easy math for me to do. I can do a /24. I know it's a dedicated subnet between all these interfaces instead of having to go through and do like a /30. It's also it takes longer for me to type in a /30 subnet mask than it is a /24. So it also optimizes my time just a little bit. So those type of things come into play. So now we have that. I'm going to go over here to, and I'm going to save that config. And I'm going to jump over to 50. And I'm going to go interface eth1/5 and set the IP address here to 10.41.50.50 and no shut. I'm going to do a show interface status. The interface is now up. We're in good shape. Now I'm going to jump over here to Catalyst, so switch 7 and switch 8. I'm going to go to interface gig 1/1, and if I do show interface status, you're going to see that it is currently connected on VLAN 1. So it's a switch port. So I'm going to type in order to take a port between a layer 3 interface and a layer 2 interface on a layer 3 capable switch, is by typing in no switch port. So now if I do that again, now it says it bounced the interface. Now it is routed. I don't know if you caught that, but it's routed right there. So I'm going to go ahead and type in IP address. In this case here, it's going to be 10.7.41.7/24. Do show IP interface brief, and I'm going to go ahead and save that config. Same thing with 8. I'm going to go to interface gig 1/1. Do show interface status. I'm going to say no switch port. And then I'm going to say it'll bounce the interface by changing its mode. And then IP address here will be 10.8.49.8/24. So do show IP interface brief, and we're good to go there. All right. So that is it for this initial configuration process. So that's that. So now that we have everything configured, we'll be able to go through the steps of getting everything working. So in the next video, we'll go through and we're going to start out with EIGRP. I'm going to get EIGRP working completely in this environment and get it completely operational. We'll walk through the configuration of all the different pieces of equipment. We've already done some basic stuff. We're going to continue doing that, but we're just going to make this a little bit bigger. And in between this video and the next video, I'm going to go through and I'm going to allocate a loopback address range for this range. So I'm going to put that probably somewhere up here, make mention of it. I'm going to configure, I'll pause the video, I'll configure the loopback. I'll show you how to configure some loopbacks on some other pieces of equipment. And then once we have that in play, then I'll walk you through, because that'll be our router ID. And we're going to need a dedicated router ID for that to work. So that's basically how that comes out. So for those of you that have any questions, comments, concerns, please drop a comment in the comment section below. If you haven't already done so, please like, share, and subscribe, and I'll catch all of you fine people in the next video. How's it going, everybody? And welcome back to our Cisco Enterprise series. In this video, we are going to cover first hop redundancy protocols, or FHRPs. Now, this is going to be a topic that is going to be more of a service than anything else, but we definitely need to go over it when it comes down to how HSRP, how VRRP work. There's a third one out there called GLBP, but we're not really going to discuss that too much. I've only seen it deployed once in production, and it was actually the wrong solution for this for the environment. And so when I see stuff like that, I do make mention of things like that. So what we're going to be doing is going through how HSRP works, how VRRP works, and I'm going to do a little bit of whiteboarding on how the back and forth communication operate, and then we'll go from there. So I will be doing an implementation of both. I'll do HSRP on Catalyst, and I'll do VRRP on Nexus. So you should see the difference between the two. So first off, redundancy protocols. So what is the goal? Is to implement virtual default gateways. So multiple gateways have the same virtual IP address, and end hosts use the virtual IP as their default gateway. only one router responds to ARP requests for the virtual IP, and ARP response contains the virtual MAC address. If the active gateway fails, the backup becomes active. Failure detected via a keep alive protocol, so usually like a hello, something like that. The backup takes care of the virtual MAC and IP address in the event of a failure. So essentially what's going to end up happening is we're going to have two different devices. We're going to have, move my keyboard over a little bit. You're going to have R1 and you're going to have R2. On this, I'm going to draw a line here, and these guys are going to be connected to a LAN segment. And then downstream of this, you're going to have your, PC1, PC2. Let me draw it this way, actually, a little cleaner. So we're going to draw a handful of PCs out. Right, so we'll do PC1, PC2, PC3, and then PC4. What will end up happening is these guys will communicate, and for anybody that's curious as to what this line is right here that I've drawn back and forth, this is to signify that it's a layer 2 connection. So you've got a switch sitting in between the routers and the PCs, and the PCs are connected to the switch, the routers are connected to the switch. Now, this could be the same physical switch, or it could be multiple individual switches, and you're doing trunking between the two. So how the actual, as long as you can get layer 2 connectivity between R1, R2, and then all of your PCs, that's essentially what you're looking to do. What will end up happening here is you're going to end up grabbing an IP address, and the virtual IP address is also known as the VIP, and then you have this virtual MAC address, or the VMAC. This is going to be a combination of information. This combination of information is how your endpoints are going to point to the virtual IP address, which, think of this as going to be sitting right in between both devices. They're going to share it. However, whoever gets elected as the active forwarder, that is who is actually going to own the MAC address. So the VMAC will be associated to one of the devices. When you have that situation, whoever the active forwarder is, that is who is going to respond to your ARP request. So if PC1 sends out an ARP, we send an ARP request out, like, who is my default gateway? Who owns 10.1.10.1? Well, what's going to end up happening is the active forwarder is going to respond with the MAC address of this, if we're dealing with HSRP. The first part of this right here, split this down the middle, all of this, if you see 0000.0C07.AC, that is going to indicate that that's HSRP. That's how you're going to know that. If you see down here, if you see 5E, you're going to know that that's VRRP. So that's going to be the difference between the two. This portion of the MAC right here, the XX, that is going to be indicative of the group number. So what will end up happening is, on a per VLAN basis, you're going to go through and you're going to configure HSRP per SPI or per subinterface. So for a SPI, we're talking layer 3 switching. That's going to be an SPI. For router on a stick, actually I should say router on a stick, that's going to be your subinterface. I'm just going to put subint. The subinterface or the SPI, regardless of how you want to do your deployment, regardless of which routing mechanism you go with for first hop redundancy, whichever mechanism you go for when it comes to gateway routing, whether it's router on a stick or layer 3 switching, regardless of which way you go, you still need to associate on a per VLAN basis what the group is going to be. And typically you're going to associate the group is going to be based off the VLAN ID. So if I'm going to say the group is going to be equal to the VLAN, and this is how you differentiate. The last thing you want to do is say standby 0 and then set the IP to be 10.1.0.1. because that means literally everybody is going to be using the same gateway. So don't do that. Don't use 0. 0 is a bad thing. It's available, but don't use it. So the one thing about HSRP is it is a Cisco proprietary protocol, and therefore it does take some, you have to run it only on Cisco gear. Get back over here to my pen tool. So it is Cisco proprietary, and it elects an active gateway based off of priority. By default, the priority is 100, and the 256 is the maximum. The highest IP is the tiebreaker, non-preemptive by default. So when you get into situations like this, even though 100 is the default, the higher IP is the tiebreaker. Now here, the key factor here is if you have a higher IP, if you go based off of the IP address, so let's say this guy here is .1, this guy's over here is 2, right? Which one of these devices would automatically become the active forwarder? And the answer to your question is, well, 2, right? Because it's got the higher IP. But what happens if I want R1 to be my active forwarder? Well, simple. I'd have to go and underneath the group standby 10, for example, I'd have to set the priority to a higher value, which would then allow me to have R1 then become the active forwarder. And priority is how that happens. So that's essentially where that comes into play. So non-preemptive by default. What does preemptive mean? Preemptive means that in the event of a failure, R1 will fail over to R2 because R1 will have a higher priority. So actually, let's go back to a scenario where you're using R2 has a higher IP, so he's got the active forwarder. You're not doing any prioritization. If I go to priority, or I'm sorry, if I don't have priority in place, I'm doing 100 as the default, router 2 is a tiebreaker. So if R2 were to go down, for whatever reason, R1 and R2 are sending information back and forth, and they're using UDP UDP multicast to 224.0.0.2 at port 1985 for transport. So it's blindly sending the traffic in the blind, right? It's sending multicast hellos to that address via port 1985, and if it gets a response back, great. Now, it uses 3 hellos, and so it's a 10-second failover. So you have 3 and 1 partial fourth before it'll trigger. So you miss 3 full hellos, so 9 seconds. In the 10th second of a failure, once it detects it, it's going to automatically flip over. So if R2 goes down, HSRP will wait 10 seconds before R1 will take over. R2 is not there, R1 will end up taking over after 10 seconds, and then your endpoints will start being able to forward again based off of R1. R1 will then be responding to all of your ARP requests and things like that. Now, in a layer 2 environment, when you have your upstream devices, if everybody was using an active uplink towards R2, and then R2 fails, and then you flip over to R1, you are going to have to do a really quick spanning tree recalculation to figure out the new uplink. If you're doing rapid spanning tree, it's going to happen like that. If you're doing PBST, regular 802.1d spanning tree, it's going to take you some time. So just keep that in the back of your mind when you're discussing, your layer 2 architecture and stuff like that. Now you can do authentication if you'd like to do so, and we can take a look at that as well, but it would just be a simple password. It supports multiple groups per interface. So you would have the MAC address is automatically generated when you turn the capability on, so it's going to generate this MAC address right here, and then where the X is going to indicate the group number or the VLAN. HSRP may use object tracking. Now, what exactly is object tracking? What is that? Well, instead of a scenario where the upstream, and this is more or less for you're trying to make sure a certain next hop is working. So you might be in a scenario where the local interface might not ever go down. So physical connectivity might never be broken. So you need some way to track, when do I consider this a failure? So if you are pinging a particular next hop IP address, and typically you're going to ping the next hop up physically next attached to you. You might not be layer 2 adjacent to it, or there might be a scenario where it doesn't make sense to do rely on link state. So is the interface actually up and operational? If your router connects upstream through a switch to then another device northbound of that, then you can't rely on link state itself. Because if the upstream device, so let me draw this out actually really quick. If you run into a situation like this where we have R1, we have R2, and these guys have, there's a couple switches here in the middle, and you've got some switches like this. So R1 and R2 connect in here. These guys are connected like this. There's a port channel between the two. And you got connectivity like this, like that. And then upstream here, we've got a couple more switches. So these guys connect up to here, and then you have, say, ISP1, you have ISP2. Well, these guys connect up here like this, and maybe there's a connection between these two guys. The switch ports themselves are not going to be, because then you have a scenario where R1 and R2, maybe R1 and R2 are, you can't rely on link state alone when you're not physically running the cable from one device to another. That's going to be your actual uplink. You might have a scenario where you can't do that. And if you can't, that's fine. But so actually another scenario that comes into play is, let's say we have only a single ISP. So we get rid of ISP1 or ISP2. Let's say we have only a single ISP, right? ISP1, but we want to do redundancy here. So what we'll do is we'll take ISP1's single internet connection and we'll terminate on one of these devices, right? We'll do that, or maybe we only have, let's say, for the sake of argument, we're going to say we have one switch, right? It's a stack. It might be this stack right here and this set of switches right here might be the same pair. You can do that too, and I'll talk a little bit about that more in detail. Where, well, the simplicity of it is, when you're doing something like this, you need to just carve out another VLAN on this pair of switches. So this pair of switches and this pair of switches might be the exact same physical pair, but you just created another VLAN and put a couple of ports into that VLAN in order for you to do your internet routing. So completely doable, a very well-defined design. So what ends up happening is you have ISP1, and let's say you're doing, this guy's got an IP address here of .1, and it's a /30. So what you would do between these guys is you would do HSRP on, so both down-facing, and you would do upwards. So you do HSRP here as well. And you would give, the service provider would give you the IP address, look, depends on the scenario, but you would tell the service provider to point to the virtual IP address, and it would go back and forth. Sometimes it works, sometimes it doesn't, it depends on the design. A /30, you're really not going to be able to do that because you need three IPs for that to actually work. You need one here, and then the actual VIP. If you have a /29, that'll work because you need 3 usable IPs. So, the provider's got one, you give one to each one of your devices and then one VIP, and then you have the provider point to this. But I'm getting a little too far in the weeds. Like I said, I've done a lot of internet edge routing. This is where my brain goes. So, regardless of how you have it set up, there's going to be a shared connection. So there's going to be an IP address shared between these two boxes. And what will end up happening is, from a link state perspective, going back to that, if you have a scenario where this interface goes down, this switch port will go down with it, but it's not going to translate that to this connection or this connection because the switch doesn't care. The switch isn't going to pass on a link state. I think it's called link state. So it's not going to pass that information through. So rather than you relying on the link state of the upstream interface, what you would use then instead is you'd use object tracking, where you would create an IPSLA. So your IPSLA, let's say you're pinging this IP address right here, whatever that IP might be. let's say it's going to be 81.1.1.1. So you have 81.1.1.1. You create an IP SLA. SLA stands for a service level agreement, and which is basically just an operation. It's just a consistent ping, but there's a lot more things that you can do with it. A ping is one of the basic things that you can do. So you're basically just pinging this IP once every 5 seconds or something like that. And as long as you get a response back in, you're in good shape. And then you need to miss three pings in order for it to fail. So you're giving yourself 15 seconds to fail. And then if it fails, then you're going to fail over to this interface. Normally what will end up happening is you're going to have two different service providers, and if you have that situation come into play, you're going to be pinging an upstream provider, and if that IP fails, then you're going to swing it over to this guy, and you're going to stop. You're going to tie that to a static route. But we haven't gotten into reliable static routing. We haven't gotten into any of that yet. So that'll happen down the road. I just, at a high level, and I've actually taken it way further than I wanted to, so that's my fault. What you'll end up doing is, with the IP SLA, is you'll have it ping the upstream IP address via like a static route, or you'll be doing some upstream tracking to where if you've got, and actually let me clean this up just a little bit because it's getting a little too messy. So if I have a connection like this, where we'll go back to the two service providers design, because that'll make more sense. If I have ISP1 and I have ISP2, and these are both directly connected, well, actually, let's say there's a switch in between again. So let's say there's a switch in between. You'll connect R1 and R2 to this guy, and then they'll connect in here. You have a dedicated two different VLANs, one for each connection. Because the link state does not get passed through from one switch port to the other, you would create an IP SLA to track this IP here, and then you would tie that to a tracking object, and the tracking object would then get tied to HSRP. Same thing with here. So if you're tracking this IP SLA to ping this IP address right here, tie that to a tracking object gets tied to HSRP. What will end up happening is, in the event that you're pinging this IP address and it goes down, let's say this guy's the active forwarder. If you're pinging this guy right here, then you'll start pinging it. If the ping fails, if ping fails, IP SLA fails, enhanced object tracking, the track fails. If the track fails, then HSRP fails, and then you transition over to this guy. Now, normally speaking, you wouldn't do this on both sides. You do it on one or the other. A primary, the internet connection that you want to use would have that set up, but you could theoretically do it for both. In a real-world design, you're going to pick the provider that you want to send all your traffic out, and then you're going to pin it to one upstream provider, and then you're going to fail over if there's an issue. However, there are preemption capabilities that come into play where you don't want to preempt back, stuff like that. But that we're getting too far into the weeds and how it all comes together. All preemption means is this: if there's a failure in the network with HSRP, R2's upstream interface to the ISP2 goes down, router 2 fails over to R1, R1's doing its thing. When ISP2 comes back online and the SLA is passing, in other words, it's getting responses back in from the upstream provider, then tracking is good, then HSRP comes back online, R2 is good to go. Then after a period of time, R1 will pass that connection back to R2, and then R2 will start sending traffic again. So preemption means, let me take back what I had before. That's all preemption means. So keep that in the back of your mind. So you can do some additional configuration. You can authenticate and stuff like that. I've never really had a scenario where I've ever had to authenticate, but that just really goes into the piece where if you want to, go ahead and do it, but in most cases, most customers don't, but there's no reason why you can't. So beyond that, that is going to be how HSRP works at a high level. Now VRRP, I'm going to go ahead and clear the screen. VRRP works very, very similar to that. So it is the open standard version of HSRP. And the only thing it does differently is it does master and backup as opposed to primary and standby. And other concepts are similar, preemptive by default. So it's automatically going to preempt unless you tell it not to. And then it uses a different MAC address, 0000.5e. If you see this show up in your MAC address table as an ARP response, you're knowing that the upstream connection is HSRP enabled, and then you can do all that. So it's very, very simple in order to configure. So I'm not going to get into GLBP at all because I've only seen one customer use it, and it was the wrong use for GLBP. This is more for when you have multiple gateways, you have different groups, you're going to have different MAC addresses generated for it. But GLBP, no customer that I know is running it, and they normally wouldn't. So to me, it doesn't add any value in terms of that. So that is basically that. So now that we've talked about those details and we've gotten a little bit of tracking, I'm not going to be doing any tracking demos in this video, but what will end up happening is in follow-on videos, we'll be taking a look at tracking and how that'll come into play, because I want to do some basic tracking of internet reachability first before I do first hop redundancy. But once we get into, because we're near that, once we get through some of the EIGRP processes and we do high availability on the internet edge, and we talk about that, it'll get more things squared away down the road that we need to have in play. So my plan is to, and I'll actually show you what I mean. When we look at this part of the network right here, I'm planning on doing some internet high availability, where we have two different service provider connections, AS1, AS3, and we'll do some testing to fail over. We'll do a floating static route to make ISP3 the backup to ISP1. ISP1, we have a whatever higher speed internet connection, or whatever the case might be, whatever scenario you want to throw at it. And then our AS2 is going to, or I'm sorry, AS3 is going to be the backup, something along those lines, or vice versa. And we'll take a look at how that comes into play and go from there. But that's essentially what I wanted you guys to see and understand, because it can get complicated. As you can tell, I didn't want to get to a super deep explanation of how any one particular first hop redundancy protocol worked and all of its little nuances without doing a demonstration of it, because sometimes it might be hard to follow along or to stay on track with it. So that's going to be that. So what I am going to do in the next video, because now we've got everything, so we're going to go configure HSRP, and then after we configure HSRP in the follow-on video, what I'm going to go do is we're going to go and stand up EIGRP throughout this entire environment and get it fully stood up. So everything from iOS, iOS XE, XR, Nexus, we're going to get these guys involved. We're going to talk a little bit how that comes into play. We're going to talk about some capabilities, some features to help control where you're forming EIGRP adjacencies and things like that. Get all of this connected and all this configured for EIGRP, so we have full functionality and all the stuff that goes along with that. So if you guys have any questions, comments, concerns, feedback, drop that sucker in the comment section below. If you haven't already done so, please like, share, and subscribe, and I'll catch all of you fine people in the next video.